the detailed procedure of hypothesis testing we will discuss in detail, because hypothesis testing is the most important part of our econometric analysis. Hypothesis testing is the most important part, okay? Because there only you are going to if you recall what was our objective of econometric analysis, drawing inference about the population parameter. And how do you draw inference about the population parameter? By checking whether the coefficient of income is statistically significant or not. If the coefficient is statistically significant, then we can say that income has significant impact on consumption. That is the inference what we are going to make about our population, okay? And that is not possible after estimation. For that we need to go for hypothesis testing. That is why we say that econometric analysis is mainly divided into two stages. One is estimation and another one is called hypothesis testing or inference making. So, the hypothesis testing is the most important part for this inference making, and that is the reason we need to discuss in detail about hypothesis testing. That we will discuss in detail in our later part of our discussion. Now, once you go for hypothesis testing, then if you recall, what is our next step? Forecasting. Instead of forecasting, I would say prediction, since we are going to use the cross sectional data. So, that means with hypothesis testing, now you have established that yes, my beta hat is significant not only mathematically, but also statistically, because I have now ensured that even if I collect another sample, my beta hat value will be significantly different from 0, and it is not by a chance factor, all right. So, that is why you can now use this alpha hat and beta hat value for prediction. That means, now you can use this model to predict what is going to be somebody's consumption for a given level of income, or you can also predict what amount of income is required to sustain a specified values of consumption. And these estimates then now can be used for policy making. But before we use this alpha hat and beta hat for policy purpose or prediction or forecasting purpose, econometricians they say that you must ensure that your alpha hat and beta hat, the estimated the estimates of your population parameter, they exhibit 3 desirable properties, okay? 3 desirable properties before we actually use them for policy purpose, forecasting or prediction. For example, let us say you have invented a vaccine for the ongoing coronavirus, but before we apply that medicine on the human being, you need to examine whether this vaccine is reliable and whether this vaccine is having any side impact or not, okay? Like that, our estimates of alpha hat and beta hat also, before we actually apply for policy purpose, we must ensure that they are reliable and they exhibit certain desirable properties. Unless they exhibit those desirable properties, it would be dangerous to use this alpha hat and beta hat for policy purpose, like applying the coronavirus medicine on a human being without testing their desirable properties. And what are those desirable properties of your alpha hat and beta hat? There are basically 3 properties that your alpha hat and beta hat must exhibit. What are those? First one is called efficiency, okay? Efficiency property. That means efficiency is defined as the variance of your beta hat should be minimum. Now, I will explain this. Variance what is say that efficiency property, this is desirable properties of the estimates. First one is called efficiency. Which basically says that variance of beta hat should be minimum. Now, I will give you one example that will make your understanding of efficiency very clear. Let us say this is your true population parameter, which is beta, and I am giving an example. Sometimes we play a game, let us say this is a point what we are targeting with a gun. So, that means we have to hit this point, and if you shoot, if you make 100 shoot, let us say you are making 100 shooting, then in all your 100 shooting what will happen? Sometimes you will hit exactly here in the beta, sometimes you will hit here, you will hit there like this. And let us say that all these points are beta hat. This is, let us say, beta 1 hat, this is beta 2 hat, beta 2 hat, beta 3 hat, beta 4 hat, like that. These are all points. So, that means what basically this minimum variance property say that in all your shootings, the variation, the deviation from the actual, from the point should be minimum. Then only we can say that these estimates of true population parameter beta 1, beta 2, beta 3, they are actually reliable. But suppose your point is here and you are targeting here, that means you have a huge variance, and I cannot rely. Today you are hitting here from this sample, and next if I collect another sample, that beta hat is here. So, that means when my objective is to draw inference about the true population parameter with the sample statistic, my sample statistic should lie as close as possible to the true population parameter beta. Then only we say that there is preciseness in our inference. Otherwise, if your estimates variance of the beta hat is too large, that means you are basically hitting like this. This is your beta, and your beta 1 hat is here, beta 2 hat is here, and then this is beta 3 hat, then it is beta 4 hat. So, this is situation 1, and let us say this is situation 2. So, I will say that minimum variance property will be satisfied here in this context, where variance of my beta hat, that means when I am collecting several samples from the population, I will get a variance of beta hat, okay, variance of beta hat, and that variance is basically should be minimum. That is the desirable properties. Why this is required? Because when the variance is minimum, there would be preciseness in our decision making, in our inference making. When the variance is much wider, much larger, then there won't be any preciseness in the inference. That is why minimum variance property says that variance of beta hat should be minimum. But the way we have explained this case, it appears like we are going to draw 100 samples from from the population, and we will estimate 100 such beta hat values, and then we will compute that variance, and then we will check their efficiency property satisfied or not. But actually in reality we will collect only one sample, we will only estimate only one beta hat, but we will ensure the minimum variance property. Why? How? Because of a statistical procedure. If you recall that we have assumed that yi equals to alpha plus beta xi plus ui, and we have assumed something about this ui follows a normal distribution. When ui follows a normal distribution, that will ensure the beta hat will also follow a normal distribution, and that variance of the distribution I am talking about. So, you need not collect, you do not have to collect 100 samples, we will collect only one sample and estimate only one beta hat, but we will ensure the minimum variance property. We will check the minimum variance property of that beta hat whether it is satisfied or not from one sample only, because of the distributional assumption of this ui. Okay, we need to ensure. And the minimum variance property would be satisfied only when we estimate our model under certain assumption, and those assumptions they basically explain an idealistic situation. Okay. What are those assumptions? That we will discuss later. For the timing, you just keep in mind that there are certain assumptions that we must make to describe an idealistic situation under which when we estimate the model, our beta hat value will show the minimum variance property, that is called efficiency. Then the second property, desirable property that we also need is unbiasedness. This basically says that expectation of beta hat equals to beta. That means when you collect several samples from the population, there would be fluctuation in your beta hat value because of the sampling fluctuation. Okay? But if you take mean of all those beta hat, that would be equals to your true population parameter beta, and that is what is called unbiasedness property. So, that means average of all your beta hat is beta, and once again I am not going to collect several samples, rather I will collect only one sample, but because of that statistical property and because of those assumptions that we make, that will ensure whether beta hat expectation of beta hat equals to beta or not. Okay? So, we must ensure this property is also satisfied before we actually use this beta hat for policy purpose or inference making. That is called unbiasedness. Okay? Unbiasedness. And then the third property is called consistency. Consistency property is little involved. I will explain step by step. Let us say that you have estimated your beta hat value as this and your true population parameter is this. So, the difference between these should be minimum. Okay, should be minimum. That means it should be less than delta, where delta is a very small quantity, smaller than whatever you can actually imagine. So, that means beta hat is very close to the true population parameter beta. And what is the probability of getting such beta hat? Probability of getting such beta hat, okay, equals to 1 minus epsilon, where epsilon again is a very small quantity, smaller than what you can actually imagine when your sample size tends to infinity. So, this is the consistency property. So, if you think step by step, you can easily understand. Your beta hat value is the estimated value of the true population parameter. Beta is the true population parameter. So, the difference between beta hat and beta should be minimum. That is why I said the difference is actually lower than delta, where delta is very small and smaller than what we can imagine. Similarly, epsilon is also very small and smaller than what we can imagine. Okay. So, that means probability of getting such beta is almost 1, and when will that happen? When sample size tends to infinity. So, that means this consistency, while unbiasedness and efficiency you can ensure in a small sample also, consistency property, or it is also called asymptotic property, is satisfied only in large sample. Right. Okay. So, it is called asymptotic property, which is satisfied only in large sample. So, that means our beta hat, alpha hat and beta hat, they should satisfy efficiency, unbiasedness, and consistency. And when will our alpha hat and beta hat will satisfy this property, these three property? When we ensure certain assumptions based on which our model is estimated. So, we have to make certain assumptions, and those assumptions will actually ensure that your beta hat and alpha hat will satisfy efficiency, consistency and unbiasedness. But in reality, when we are collecting the data and estimating the model, it is quite likely that either one or more than one of those assumptions are violated. And when the assumptions are violated, then either one or more than one desirable properties of your estimates will also be violated. Your alpha hat and beta hat will not satisfy efficiency, unbiasedness and consistency when the assumptions of that idealistic situations are also violated. Okay. That is why when we estimate the model, we have to specifically check whether any of those assumptions are violated or not. If violated, then we have to apply appropriate remedial measures. Those things we will discuss in a later part of our discussion. So, right now what we have discussed is these are the properties they must satisfy, they must exhibit before we actually apply this alpha hat and beta hat for policy purpose. Okay, for policy purpose, that is what is mentioned here. All right. So, this is what, these are the desirable properties. So, with this we are closing our discussion of this module. Basically, in the last two lectures, what we have discussed is the introductory part of econometrics, the definition, different steps, and what are the three desirable properties that our estimates must exhibit before we use them for policy purpose, right. What are those assumptions and what is the actual procedure of estimation and hypothesis testing, that we will discuss in our next class. Thank you.